All right, so today we're going to cover the very final topic of chapter number 1. This is called inverse functions. You're going to notice this is a little bit different from what we've done the last couple of days, but we are going to start with a review of that, but then you'll see what I mean. Hold on, let's get going. So we'll start with a quick review of combining transformations from last class. That's where we took going left, right, up, down, stretching it vertically, stretching it horizontally, reflecting it, all of those different things. We threw them all together in one. We are going to do a review of that. Then we're going to introduce inverse functions, which are functions that undo whatever an original function did. So if a function originally was like x squared, the inverse of the function is going to undo that. You can probably think in your mind what that might mean. We'll look at finding the inverse of graphs, tables, and equations. There's a little bit of a different technique for each one, but it's same idea overall. And then, of course, we'll get some practice time in. So like I mentioned a moment ago, this is the last concept of chapter 1. And it is a bit different than the other concepts we've done so far, but you might be able to determine some similarities. It's not exactly totally out of left field here, but you'll see what I mean. Here we go. Let's do some review first. So just remember that the general form of a transformed function is as follows: y equals a times f of b x minus h plus k. Last class, we talked about how those nested brackets, that's this stuff inside here, the nested brackets inside the function part are very important. If you didn't have nested brackets in here, in other words, if you just had like the b bumped right up against x and then minus h or plus h or whatever you have in there, just, chilling on its own, it wouldn't be quite as clear what our horizontal translation is. Like, wouldn't be quite as clear what that h is really doing. Bottom line is, as simple as I can put it, is it would really screw things up, right? So bottom line, when you have a transform function, it's always ideal to have those nested brackets if you have a b value. Just a little bit of review as to what each of these things do. Remember, a is your vertical stretch, so it's how much you're stretching your function up or down, like making it taller or shorter. B is related but not equal to your horizontal stretch. Your horizontal stretch would be 1 over B. It's a really, really weird relation there, but it is what it is. H is your horizontal shift, so this is the thing that moves it left or right. And then K, that's my favorite one, I think. That's the one that moves it up and down. I think I like it so much because it's pretty clear what that one does in the whole scheme of things, at least compared to the others. So let's do an example here. Let's suppose you had a function g of x equals x cubed, and it was transformed into a new function p of x. Just by the way, these names, they're just a name, right? So usually I use f of x. We're just switching it up here. It's not the end of the world, right? To form p of x, g of x is vertically stretched about the x-axis by a factor of 0.25. So that's a vertical stretch. Keep that in mind. It's reflected across the y-axis. Now hold on just a second. If this is the x-axis and this is the y, if you're reflecting across the y-axis, we can call that a horizontal reflection. So keep that in mind as well. And then it's translated 3 units to the right. Write the equation of the new function p of x. Now, if you want to give this one a try on your own, by all means, you can pause the video right here and do so. But otherwise, I will go over this. And if you did or didn't, it's up to you. What I would do to write a new function is, even though it's asking for like the equation of this, so equation notation, I would just start with function notation. I cannot stress enough how important function notation is. Function notation is just where we write it out using that general form that we had on the last slide. Like if I go here, it's just where you write it out using this. You just fill in A, B, H, and K. Everything else, including the F and all like the brackets and stuff, that all stays put. You just fill in A, B, H, and K. If you have it in function notation, it's a lot easier to jump into equation notation right afterwards. So in function notation, we need to find our A, B, H, and K. A is your vertical stretch. This question straight up told us what our vertical stretch is, 0.25. So I can start by saying y equals A, which is 0.25, and then F. Then we want to write our B value. Now, here's what's funny. B is related to your horizontal stretch. This question didn't mention anything about a horizontal stretch, but it did mention a horizontal reflection. If you have a horizontal reflection, that just means your B value is going to be negative. So the fact that we didn't have a stretch means B is 1, but the fact that it's a horizontal reflection means B is actually -1. So I'll write -1 in there. Then my nested brackets, as infamous as those are. Now we have to focus on whether we're going left or right. Well, the question told us it's going 3 units to the right. That means h is +3, which, as backwards as this sounds, means we have x minus 3. Bottom line is, if inside the function you have something minus a number, you're going to the right. If you had something plus a number, you're going to the left. But h is actually a positive number here because it's supposed to be x minus h. Hopefully that makes some sense. If it doesn't, please make sure you talk to me. Anyway, we'll close off those nested brackets there. And then plus k, my favorite one, up and down. Doesn't look like we have any up and down in this question. So guess what? That's now it. Now, for the actual equation notation. This is what the question wanted. It wanted an equation. The actual equation notation here is where we take our function notation and turn it into an equation using what we knew about our original function, which in this case was actually g of x. So I guess I should have called this, instead of f, I should have called this g. It is what it is, right? Bottom line is what we do, or at least what I do, I'll speak for myself here. When I go from function notation to equation notation, I always start with the innermost stuff. So I talk about what's actually inside these brackets here inside the function. The stuff that's in these brackets, not even just the fully nested ones, even just like these square ones, this stuff right here that I underlined is going to replace our x in the original function. So I'm going to start there. I'll say, I was going to say y equals, but I guess our new function is called p of x. So I'll call it p of x equals, I'll give myself some space because I know this thing's going to have to sit out in front. Give myself a little bit of space here. This chunk is going to go inside where x was. So this becomes -1 times x minus 3. That's my x. Notice x was cubed, so I'll cube it now. So it was like our x cubed. Our x is now just replaced with this. And then any other stuff that's going on, well, I guess it's just the 0.25, which is going to hang out on the outside right here. So bottom line is I replace this stuff inside the function first. If you had more than one x, like if this was x cubed plus x squared, you'd have this cubed plus another one of these squared, right? You just replace all the x's with whatever was in there. And then I finished off, of course, by putting the a value out in front. So there it is. We're all good to go. That right there, perfectly acceptable answer. As a matter of fact, I would prefer this one because it shows clearly we have a horizontal reflection and that we're going right 3. However, if you're kind of a stickler and you say, hey, no, you know what, I want to double dip this through, there's nothing really wrong with it. It's just it's going to make a form that's a little more confusing. So if you wanted to, you could double dip that -1 through and you could have p of x equals 0.25 times -1x plus 3, because -1 times 3, or -1 times -3 is +3, and then squared like that. That's totally acceptable. Personally, myself, because there's no nested brackets, I look at that and I kind of roll my eyes, but it is what it is. Either one of those can work as an answer. All right, here's another one. This is still review here. The graph of y equals f of x is shown. Quite a weird graph there, right? Now it says sketch the graph of y equals -1/2 f of 2x minus 3. If you want to try this one on your own, go ahead. But other than that, I'll go over it. So since this is such a strange graph, like this is really weird. There's a bunch of weird points going on here. I think the best way to go about this is to pick some of the key points on this graph, maybe like the x-intercept and maybe this little peak here, and then maybe this point here. Pick some of those key points and then transform them using mapping notation. So mapping notation is where we had like x, y become something. I think that'd be the best way about going about this one. Before we get to mapping notation, though, it's always a good idea to write out in words what kind of transformations are occurring to your graph. Well, let's have a look. We have the function notation right here. Notice the a value out in front is -1/2. The negative means we have a reflection. So I'll say that first. We have a vertical reflection. And then the a value itself is 1/2. So we have a vertical stretch by 1/2. So we're going to make it half as tall, in other words. We have a b value of 2. Remember, that's related but not equal to your horizontal stretch. So it's a horizontal stretch, not of 2, but of 1 over b, which is 1 over 2. So it's a horizontal stretch also by 1 over 2, and that's because of that 2 there. And then this -3, my favorite thing in the world, the thing on the outside there, that just means we're going down 3. What you see in words is what you put into your mapping notation. So our mapping notation, we'll just do it right here. Our mapping notation is going to be xy becomes, think about what's happening to our x. Well, it's none of this vertical stuff and it's not this down 3. The only thing that's happening to x is our horizontal stretch by 1/2. So you're going to be going 1/2 times x, comma, and now we have to think about what's happening to our y. Well, we have a vertical stretch by 1/2, but it's also being reflected. So guess what? You just use the -1/2 and multiply that by y. But then we're also going down 3. So then I'll say -3. This mapping notation that I wrote here is going to be really, really useful for moving some of these key points. The more key points you pick, the better. But I think really, if we're going to kind of slim out on this one, I'll just say this is a key point, this is a key point, and then this one, and then this one. I wouldn't pick this one in between. You could if you wanted to, but I wouldn't because it's a straight line anyway. Whatever, right? So these points plus, you know what, just for fun, we'll throw in this other x-intercept right here. It'd be a good idea. If you wanted to pick more points than that, by all means, but I think those 5 points I just picked there would be good enough. I'm going to use these 5 points on our original f of x as x and y, and I'm going to change them into our new function to get this transformation going. So here's what I mean. Let's take this first one. This first one is negative 5, 0. So negative 5, 0 is going to transform. I'm going to use this right here. 1/2 times negative 5 is negative 2.5. And then negative 1/2 times y, well, that's negative 1/2 times 0 is 0, and then 0 minus 3 is negative 3. So I have a point, negative 2.5, negative 3. I'm going to plot that right away, just so I don't forget about it, right? So negative 2.5, negative 3, that would be about right there. Next point I'm going to plot is this one, negative 4, 6. So negative 4, 6, if I'm going to transform it using my mapping notation, that becomes negative 2. And then negative 1/2 times 6 is negative 3. Negative 3 minus 3 is negative 6. So once again, I'll plot that right away. Negative 2, negative 6. That looks like that's going to be right there. So that's that little peak point has become this point down here. Now this next one I'm going to graph is negative 3, 4. So negative 3, 4. Transform that. Negative 3 times 1/2 is negative 1.5. 4 times negative 1/2 minus 3. So 4 times negative 1/2 is negative 2. Negative 2 minus 3 is negative 5. So we have negative 1.5 and then negative 5. That's kind of a strange point, but I'll plot it. That was that guy right there. Next point I'm going to plot is 3, 4. This one's very similar to the other one. 3, 4. This is going to become 1.5. And then we know what happens when we work with 4 here. So it's going to be negative 5. That really is convenient. So 1.5, that's over here. And then negative 5, that's over there. Cool. So I plotted that point. And then the last point we have to do here is 5, 0. So 5, 0, if we do 1/2 times 5, that gives me positive 2.5. And then 0 times negative 1/2 minus 3, well, that's negative 3 again. So 2.5, negative 3, that looks like that would be about right there. Okay, so a whole scatter plot of points here. Let's connect them with the lines. Maybe I could have done that as I was going. It is what it is. This one to this one, and then this one to this one. This one was just straight across, and then this here. And then just to really polish this off, notice in this arm, it keeps on going. So you know what? I'm just going to keep that going. If you have a ruler, you can make it even straighter. I think that's going to be good enough. And then same with this one here. Again, if you have a ruler, you can make it straighter. But that is good enough for me. So what we did just there was I used mapping notation to change that very strange graph 1 point at a time. Mapping notation is very powerful for that kind of application. Really good idea to give that a shot. Anyway, next example. This is a first in this course. Buckle up, drum roll, please. Diploma exam question. Ooh, so this is pulled from a real diploma exam in the past. This number over here, this 76.9%, that actually represents how many students in Alberta got that question correct when it was put on a real diploma exam. No pressure or anything, seeing such a number like that. Read this question. I want you to give this a try. Honestly, pause the video here, give this one a try, unpause when you are ready. All right, I'm going to go over this one. There's many different things you could do here. Notice it's saying that this is f of x, and it's asking for where this graph would intersect with this graph right here. Well, this graph right here is a vertical stretch by a factor of 3. So in other words, making it 3 times taller. If you want, you could just draw that graph right on top of this one. That would be a really good strategy. There's nothing stopping you from drawing it. Or if you're really keen, you might be able to notice that since it's a vertical stretch by 3, that's just taking your x and your y. It's leaving x alone, so x is not going to be affected. And it's just multiplying your y values by 3. If we are finding two graphs that intersect, that just means that this transformation is going to have no effect on a certain point. Well, vertically stretching it by 3 moves it away from the x-axis. Points that are already on the x-axis aren't going to move, because if you're multiplying y equals 0 by 3, it's still y equals 0. So right there, you might even be able to tell, hey, the answer is just point A. But again, if you wanted to graph the whole thing, you just multiply all of your points 3 times away from the x-axis. So this guy's actually going to go off the chart. It's going to go way up here. This guy's going to go over here. This one's going to go here. This one's going to go here. And then this one's also going to go way off the chart. Really, oh my goodness, that was terrible. I was going to say really loosely graph this, but if you have a ruler, it becomes much better. There we go, good enough. Good enough, and then this, good enough, right? Anyway, that's the stretched, clearly the intersection point, the point that didn't move, that would be point A. Anyway, we're going to do a lot more of these as time goes on, but it is nice to look at them just so you can get used to what diploma exams kind of bring. They're very strange questions that they ask. Anyway, for our brand new information, 15 minutes into this video, holy smokes. For our brand new information today, we're going to cover something called the inverse of a function. Before we get there though, let me remind you what a function actually is. A function is a relation in which each independent variable, the input or x, so your x values, is associated with only one value of the dependent variable, which is your output, also known as your y. When relations are represented by a graph, we can use the vertical line test to distinguish if they are functions. What this just basically means is if you have some sort of a graph like this, we know this is a function because anywhere along this graph, if you drew a vertical line, it's only going to pass through that function once for each vertical line. There's nowhere along here where you draw a vertical line and it would pass through twice. If you had a graph that looked like this, we'll do it like this. If you had a graph that looked like that, well, this one fails the vertical line test because it passed through more than once. So that wouldn't be a function. The bottom line is though, any x value you have should only have one value of y. The vertical line test would show you a function that has more than one value of y and therefore is not a function. Anyway, an inverse function, on the other hand, what we actually care about today is the function generated if you swap your x values and y values and then rearrange for your new y value. So basically what we're doing is we're saying that our output becomes our new input and our input becomes our new output. So we just want basically a machine that works in reverse so that we can take our old outputs, put them back through the inverse machine, and we get what we started with in the first place. So the purpose of an inverse function is so you have a ready-to-use function in the event you were given an output and wanted to find the input associated with it. So again, like I just said, you just want to go backwards. In mathematics, I hate this notation, just by the way, but in mathematics, we denote an inverse of f of x by calling it f negative 1 x. The reason I hate this notation is because, if we had like x to the power of negative 1, that means 1 over x. Or if we had x to the power of negative 2, that means 1 over x squared. I hate this notation because this makes it look like we're doing the reciprocal of a function. We're not doing that. We're not doing the reciprocal of a function. We are doing the inverse. They are different. But it is what it is. I wasn't the one who made this notation. Maybe there is a good reason for it. I'm not aware of it. I would happily learn what that reason would be, but that is what it is. That's just the notation for an inverse of a function. Now, how can you tell if the inverse of a function will also be a function? Well, you can use something called the horizontal line test. If you have an original function, like let's say this is your f of x, if you draw a horizontal line and it passes through more than once, it fails the horizontal line test, which would mean the inverse is not a function. So a horizontal line test on an original function tells you if the inverse is also a function. If you already have the inverse though, like if this was actually the graph of your inverse function, once you have the inverse function, you might as well just use your vertical line test because it's still the same test. But if you didn't have your inverse and you only had the original, you could use a horizontal line test to determine if it's a function. We'll worry about that later though. That's not the main thing. Let's worry about being able to determine what the inverse actually is. Okay, never mind. You know what? Actually, we will determine the inverse function stuff first. Never mind, backing up there. So first question here, are these two graphs functions and what about their inverse? Well, let's look at the one on the left. Notice the one on the left, it would pass the vertical line test, no problem. You could draw a vertical line anywhere. It's only going to pass through once. So yes, it is a function. Well, what about its inverse? We'll use a horizontal line test. Horizontal line test looks like it's passing that one too. So yes and yes. What about this graph, this circle? Well, it fails the vertical line test. If you drew a vertical line, it passes through more than once. So this one is no. What about its inverse? The inverse of this function is not a function because if we drew much better horizontal lines than that, that's a little bit better. If we drew a horizontal line anywhere along here, it would fail that as well. So it's a no and it's a no. That wasn't exactly the most useful thing. But anyway, here we go. So how do you find the inverse of a function? Well, you can do this either algebraically or you can do it graphically. If you're going to do this algebraically, what you got to do is you have to swap your x and your y in the equation and then rearrange your new equation now to isolate the new y. So basically, if you had like y equals x plus 2, you just change that. Like if this is the original, that's the original. Now you just change that to x equals y plus 2. That's now your inverse, but get y by itself. So then you have, oh, x minus 2 equals y. Boom, there it is. That's the inverse. Cool, right? Graphically, however, if you have an original graph, like let's say this red graph is the original, you can just swap their x and y values. So for instance, we know on this graph, it looks like we have the point -1, 1. Well, if you have the point -1, 1 on the inverse graph, it's going to be the point 1, -1. So 1, -1, boom, there it is. So this point moved here, right? You just swap your x and your y. What this looks like, if you were to like visualize this, what it looks like is you just take your original graph and you are actually reflecting it across a diagonal line, which has the equation y equals x. Kind of interesting, but whatever. Now, regardless of the way you determine the inverse of a function, you may need to determine restrictions on the domain of the original function, in order for its inverse to also be a function. Generally speaking, in this course, we want to deal only with functions. We don't want to deal with things that aren't functions. Like this original graph fails the horizontal line test, and its inverse, of course, would fail the vertical line test. So this inverse, this blue graph here, is not a function, but we would like it to be a function. So what you have to do is you basically have to say, how could we restrict our x's that we plug into our original function so that when we flip this over, its inverse is also a function? Basically, what this is going to rely on is us cutting off half of our function. So in this case, if we cut off everything below here and only focused on one of these arms, right? And when we flip it over the line, we would get this graph right here. Then that would be a function, and it would pass the horizontal line test in the first place. But we'll worry about that in a little bit. We just basically want to be able to focus on how we can get these inverses graphed and then go from there. All right, so first example here, determine the inverse of the function f of x equals that in the following forms. Well, we're going to start with an equation. To get the inverse in an equation, you just swap your x and your y. Just remember f of x is often just a placeholder for a y. So if we're going to swap x and y here, this is going to give us x equals -2/3 y plus 5. But we want to do better than that. We want to get y by itself now. So let's minus 5 on both sides. This gives us x minus 5 equals -2/3 y. Getting rid of this fraction here is kind of gross. How about we times by 3 on both sides to get rid of the divide by 3 in the fraction? So if I times by 3 on both sides, I have 3x minus 15 equals -2y. And then, of course, we just need to divide everything by -2. So this gives me y equals, if I divide this by -2, I have -1.5x. And if I divide this by -2, I have plus 7.5. So y equals -1.5x plus 7.5. That is the inverse of our function. That's our f -1x. Neat, right? It's just a little bit of work, a little bit of algebra. You switch your x and your y, you go from there. Now, the second part of this, though, is a table of values. This is awesome. When you have a table of values, finding the inverse is so nice and easy. Notice we have our table, we have our x and y. The inverse is just where you swap your x and your y. So I even kind of give you a hint right here by saying it's yx. The inverse is just going to be 7 -3. This one, it's going to be 5, 0. This one, kind of funny, swap the x and the y. Well, it's still 3, 3. That's kind of neat. And then 6, 1, this becomes 1, 6. So nice. When you have a table of values, it's amazing, right? Anyway, now it wants us to graph the inverse. You can graph the original function too if you really wanted to. I'm going to be lazy. I'm not going to bother. To graph this, notice that this is a linear equation, like a y equals mx plus b. To throw back to like math 9 and math 10. The b value is your y-intercept. So we have a y-intercept of 7.5. So we know we're going to start there. And then we have a slope of -1.5, which means we go over 1 and then down, because it's negative, down 1.5. I mean, alternatively, as I'm doing this, I just realized, wait, we have a table of values. Why don't we just plot these points? Of course, right? So 7, -3, we can do that as well. 7, -3, there we are. 5, 0, there we are. 3, 3, that would be here. And then 1, 6, hey, look at that. We already did that one when I went and used my slope. We should graph these by plotting them or by connecting them with a line, of course, too. Please use a ruler if you're doing this. I know how Mickey Mouse mine always are, but again, it's because I'm using a trackpad. If I were to put a ruler on here, I know I explained this in other videos, but not so far in this course. If I were to put a ruler on my trackpad, it just messes it up even more. So it is what it is, right? Anyway, that's all I was looking for. So this graph right here is the inverse of this function. If you really wanted to graph this function, by all means, go for it. But you'll see is it is a reflection across the line y equals x. But it is what it is, whatever. All right, next question on the other page here. Determine the inverse of this function. This one, notice, is a quadratic. We have an x like a squared in here, right? So let's start by getting the equation down. We'll do the graph and stuff on another page. That's why it's not here. Anyway, so to get the equation, just swap your x and your y. Remember, f of x counts as a y. So swapping our x and y means we have x equals y plus 3 in brackets squared minus 1. We want to get y all by itself. We have to dig away everything else here first. So let's add 1 to both sides. So we have x plus 1 equals y plus 3 squared. We want to get rid of that squared, so we're going to have the square root. This is going to be the square root of x plus 1 equals y plus 3. And then to polish this off, let's minus 3 on both sides. So we have y equals the square root of x plus 1, and then minus 3 on the outside of that square root right there. So that is our inverse function. Notice it looks absolutely nothing like what we started with, but we'll see how this can be graphed. This time around, we'll get our table of values going. Again, just swap your x and your y. So this becomes 0, negative 4. This one becomes negative 1, negative 3. This one becomes 0, negative 2. And this one becomes 8, 0. Now, something I want to kind of illustrate to you on this is notice that we have 0, negative 4 and 0, negative 2. That means we have an x value, so 0, that has 2 different possible y values. Since we have one x value that has 2 possible y values, I can tell just by looking at that table of values that this is not going to be a function. It's going to be something that fails a vertical line test. Another thing that this tells me is because we have 2 different values of y for the same x, why don't we check another value of x just for the same thing? I'm going to pick this bottom one because 8 seems to be a little bit better. You would think that if 0 has 2 possible y values, that 8, when x is 8, it should also have 2 possible y values. Let me show you what I mean. We're going to use that equation that we just generated here. You don't have to write this down if you don't want to, but just kind of sit and absorb for a second. I'm going to plug in x is 8 here into our inverse function. So we have y equals the square root of 8 plus 1 minus 3. Now, of course, that cleans up a little bit to y equals the square root of 9 minus 3. And most of us, when we're asked, what is the square root of 9? You'd probably say 3. So you'd have y equals 3 minus 3, which of course is 0. And that just gives us the point we had right there. But keep in mind, when you square root a function, or rather, when you square root a number, it could be positive 3, but it could also be negative 3. So this could also be y equals negative 3 minus 3, which would give us y equals negative 6. So I guess what I'm saying here is we could also have the coordinate x is 8 and y is negative 6. So that could be another coordinate. Maybe you want to write this just below your table of values, and you'll be thanking me for this in just a second. Onto our graph, you can just use the points that you put on that table. This time around, I will graph both my original graph and my inverse graph, but I'll start by drawing the inverse one. So use those coordinates from the table. Hopefully you have them in front of you. The first point was 0, negative 4. So 0, negative 4, I'm going to put that there. And then we had negative 1, negative 3. That would be right here. And then we had 0, negative 2. Notice right there, there's that vertical line test failure right there. So that tells me it's not going to be a function. And then we had 8, 0. And then really just to drive the point home, remember I told you we also technically have 8, negative 6. Let's draw that one, 8, negative 6. Use your imagination now. If we were to connect these points, notice what the shape of the graph is. It looks like a quadratic that might have fallen onto its side. Let's actually connect those points. So connecting these points here as best we can. That's good enough. Ooh, that one's not so good. Let me try that again. There we go. Connecting those points. Nice. So that clearly looks like a quadratic that kind of fell on its side. Just to really drive the point home, oh, hold on, you know what, I'll even call this f of negative 1x. Just to really drive the point home, I'm going to graph on the same graph here, the original function f of x. Just remember f of x was x plus 3 squared minus 1. Now, if you're wondering how we can graph this, I guess in the table of values, it did give us some points. Maybe we could do that. But if you really wanted to, you could also remember that technically this f of x is in itself just a transformation of a base function x squared. It's like we moved x squared left 3 and down 1. So left 3, down 1, that gives us a point of negative 3, negative 1, which was actually on our table of values from before in that left-hand column. Filling in the other table of value points, we had negative 4, 0. we had -2, 0, and we had 0, 8. And then I think you can use your imagination here. This is just a normal quadratic. So this 8 should also be way over here as well. So we can combine all of these points by connecting them with a curved line. And oh, that was miserable. Let me try that again. There we go. That's okay, I guess. That'll work well enough. So what I want you to notice is this red function, that's our inverse. This blue function was our original f of x. All we did was we just reflected that across a line y equals x, right? So across this diagonal line here, it was just reflected. If you kind of turn your head and imagine that that dotted line there is like a mirror, we just mirrored it across that line. Now, for this next question, is the inverse a function? I think we can tell very clearly the inverse is not a function, so no. And we would have been able to determine that either by looking at our inverse function and saying it fails the vertical line test, or by looking at our original function, says that original function would fail the horizontal line test, which means its inverse is not a function. But since it's not, how would you restrict the original function? So how would we restrict this blue one so that the inverse is also a function? Well, the main idea here is we want to be able to cut off one of the arms of this original function so that we end up, passing the horizontal line test so that our inverse becomes a function. So what I mean is, really, if you were to draw a horizontal line in here, it fails because it passes through more than one point. We don't want it to do that, so let's just focus on one of the arms of our function. If we only have one of the arms of our function, if this other arm just disappeared, it would now pass the horizontal line test. Now, of course, we can't just completely ignore it, but we can restrict our domain to say, hey, you know what? We're only going to care about x values within this certain domain. To do this on a quadratic, just focus in on your vertex. Then you can choose either the points bigger than the vertex or smaller than the vertex. It honestly doesn't matter. It's up to you. I think 99% of people, though, would say, let's pick the values greater than that vertex. So if I say, if I'm going to restrict my domain, so restrict domain of the original function f of x. If I'm going to restrict the domain of f of x so that the inverse is a function, I'm just going to say that x needs to be greater than or equal to -3, which is where our vertex was. If that's the case, if we are doing something like that, that just basically means we're chopping off one of the arms of our function here. So we're only left with this piece. And then if you turn your head and you imagine that flipping over the diagonal line there, that's going to erase this bottom arm of our inverse. So it's going to look something like that instead. So if we restricted our domain to that, we would end up having an inverse that is actually a function, right? It passes the vertical line test. The original passes the horizontal line test. That's really weird, but basically the whole reason for that is we want to be able to get a function. We don't want to have something that isn't actually a function. So it's important to restrict the domain so that when we plug in an x into our inverse, it is indeed just a function. We're not going to have more than one possible value. And this is the way we do it. We restrict the domain of the original function. Anyway, let's move on. So find f of -1x of the following. Be sure to restrict the domain when appropriate. So we want to use our algebraic method here. Let's just swap our x and y's. This should go pretty quick. The restricting domain, on the other hand, that'll take a little while. Let's start with this first one. If we're going to swap x and y, this becomes x equals 7y minus 4. Let's add 4 on both sides. So x plus 4 equals 7y. And then divide everything by 7. So you can say that this is x over 7 plus 4 over 7. There's no point writing that as a decimal. Let's be real here. Equals y. There it is. Now it says be sure to restrict the domain when appropriate. Well, guess what? This is a linear function. This is like an mx plus b kind of situation. When you have a linear function, you're not going to have to restrict your domain. Linear functions will always pass the vertical line test or even the horizontal line test. So we don't need to restrict the domain in this case because it's a linear function. It's more the quadratics that you have to be worried about. If you have a quadratic, you'll have to limit its domain. Now let's worry about this next one. F of x equals x minus 8 squared. Whoa, there you go. We have a quadratic, right? Let's first start by finding the inverse. So this becomes x equals y minus 8 squared. Let's get this y all by itself. I would square root both sides. So we have a square root of x equals y minus 8. And then, of course, just add 8 to both sides. So y equals the square root of x plus 8. So that's our inverse function right there. But the unfortunate news is we need to restrict the domain of the original function. Well, here's how we can do that. Remember on that one a couple slides ago, I'm just going to bounce back. we had to focus in on the vertex of our original function. So I want you to think on this function right here, on our original function right here, think about what that vertex would be. Now, some of us might be at a point right now where you're like, oh, I'd have to throw that in my graphing calculator to see it because that's kind of hard. But think of it this way. Imagine if x squared, just plain old regular x squared, imagine if x squared was our base function here. Well, this x minus 8 squared is just moving it to the right by 8. On your original x squared, you'd have 0, 0 as your vertex, but if we're moving that right 8, we're now at 8, 0. So 8, 0 would be our new vertex. So if we're going to restrict the domain of this original function, we just want to chop off one of the arms of that function. And if our vertex is at 8, 0, if we're like way over here, chopping off one of the arms just means we need to say that x needs to be greater than or equal to 8. So for my restricted domain, I'll even write that, restricted domain. It just needs to be x is greater than or equal to 8, right? So that just means we're accounting for only the x's greater than where its vertex was. That's it, right? The hardest part about this, I think, is just identifying where your vertex was on your original function. And if you're not quite there yet, where you say, oh, I wasn't able to see that that's going right 8, you can always use your graphing calculator. Just graph the original f of x in your calculator, see where your vertex was, chop it off from there. It's all up to you. Now, this last one, number C here. Let's first start by replacing our x and our y. So this becomes x equals 3y squared minus 9. Add 9 to both sides. So that's x plus 9 equals 3y squared. We're going to want to divide everything by 3 here. So this is going to be x over 3 plus 9 divided by 3 is, well, it's just 3. So I'll just say it's plus 3. That equals y squared. And then lastly, we're going to have to get rid of the squared. So we'll square root everything. So this is y equals the square root of x over 3 plus 3. The whole thing was square rooted there, right? So that's our inverse. Now, because this original function was a quadratic, we have to restrict the domain on this one as well. But unfortunately, this one's kind of funny. You know, it might not be so clear what's happening to this function. Personally, if I looked at this and I said, okay, if we're comparing what happened to the base function x squared, personally, I'd say, all right, there's a 3 that's on the outside of the function. It's not inside the x. It's not being squared with this. There's a 3 on the outside here. So this is like a vertical stretch by 3, and this minus 9 here moved it down 9, right? Well, a vertical stretch is not going to affect your vertex, right? Your vertex isn't going to be affected by a vertical stretch, but this down 9 certainly is. So this graph of this original f of x, if it's going down 9, it's going to be way down here. It's going to look something like this. It's going to be really thin because it was vertically stretched by 3, but it went down 9. Bottom line is, I know my vertex of this function is most likely 0, negative 9. Another way you could do this, remember way back in Math 20, when you said if we had like y equals ax squared plus bx plus c, the vertex was just x equals negative b over 2a. Well, you'll notice your b in this case, the number just in front of an x is 0 because there's nothing there. So I know our x is negative 0 over 2 times 3. Well, it's just 0 anyway, right? I think personally, I prefer to think of it this way. Vertical stretch by 3, down 9. If you wanted to think of it this other way, go for it. Or as your final last resort, you could have just thrown this in your graphing calculator and found where your vertex was. The bottom line is when we are restricting a domain, you need to know the vertex of the original f of x. Do so however you're most comfortable, whether it's graphing your calculator, whether it's doing this old method, or whether it's just applying what we know about transformations. It's up to you. Anyway, enough of me rambling. If I'm going to restrict my domain here, my restricted domain, and this is of my original f of x, my restricted domain is I just need to pick one of the sides of these arms here. I always pick the positive, so I'm going to say x is greater than or equal to 0, right? Because that was the x value of my original vertex. Whew, okay, that was quite the gauntlet. These last couple questions hopefully will go a little quicker. We're almost done. It's been a long video again, I apologize. Next one, graph the inverse of each function below, determine whether the inverse is a function and state any invariant points. Remember, invariant points are the points that don't actually move. Bottom line here is when you have a graph, just swap your x and y. You can make yourself a table if you want to. Honestly, I'm just going to like pick some points and go. So I'm going to do this one on the left first. I think the first point I want to move is this right here. This little vertex piece on this would be 0, 1. 0, 1 on the inverse is going to become 1, 0. Well, that would be this point right here. So that went right there. Another point I'll graph. I don't want to pick 1 something because I don't know what that is, but how about 2, 4? See this point right here, 2, 4. That's going to become 4, 2. So 4, 2, that goes right there. Likewise, on the other side here, negative 2, 4. That's a point right here, negative 2, 4. That's going to become 4, negative 2. You just swap your x and your y. So negative 2, 4 becomes 4, negative 2. That's right there. You could go further if you wanted to, but now I can already see how this function is going to go. Might as well just connect this with a line. Oh, that wasn't very good. Try it again. That was better. There we are. Connect that with a line, and then connect this with a line as well. Good enough for me, right? So we've graphed the inverse. Now it says determine whether the inverse is a function. You could have determined that in the first place. This original function would fail the horizontal line test. So no, the inverse is not a function. And then state any invariant points. That's points that didn't move. Well, guess what? There are no points that didn't move. Everything moved here. Points that won't move are going to be points that lie on the line y equals x, that diagonal dotted line that we're reflecting it across, right? So there are no invariant points. Maybe I'll even say that. No invariant points on this one. All right, what about this next one? We want to get the inverse going on this. Personally, because this is such a really bizarre function, I'm just going to pick some points and then move them one at a time. I think I'll pick this point first. That's the point negative 7, 1. Negative 7, 1 is going to become 1, negative 7. So 1, negative 7, that point gets plot right there. Next point would be negative 4, 4. Negative 4, 4 becomes 4, negative 4. Plot it right there. And you know what? I'll connect that with a line before I lose myself here. What about this point? This is the point 0, 5. That's going to become the point 5, 0. So that's going right there. Connect that with a line as well. Obviously, using a ruler is really going to help you. And then the last one here is this point 2, 0. 2, 0 is going to become the point 0, 2. And then I'll connect that with this other one here. That's really bizarre. Okay, so anyway, we've graphed the inverse. That's about as good as we can get. Determine whether the inverse is a function. Well, notice the inverse fails the vertical line test, and the original function failed the horizontal line test. So no, the inverse is not a function. And then state any invariant points. Maybe I should change the wording on here because state isn't really going to be possible. Notice there is an invariant point. It's this point right here where the two graphs touch, right? That is going to be an invariant point. So I'll just say invariant point is right there. So invariant point right there. If I were to guess what that coordinate is, I'd say maybe it's 1.5, 1.5. Notice it's just wherever your x is equal to your y, right? Another way of thinking where your invariant points are going to be, I alluded to it on this graph, it's just any point that crosses the line y equals x, right? So anywhere that crosses this imaginary dotted line, notice that point right there, cross it. We could have determined that before we even started, but it is what it is. Anyway, last question, and this one is one of the most important ones. Hopefully this really summarizes it for us. Consider the function f of x equals x squared plus 1. Start by graphing the function f of x. So we want to graph x squared plus 1. How can you tell that the inverse of f of x won't be a function? Well, let's start by graphing it first, then we'll see. So f of x is x squared plus 1. The way I'd go about graphing this is realize that this is just taking x squared and adding 1 to it. It's just moving it up 1 point. Well, if we're moving x squared up 1 point, that just means my vertex is now right here. And then since it's an x squared function, we can just use the 149 rule to graph the rest of it. The 149 rule says start with your vertex, go over 1 and then up 1 times a. There is no a value here. There's nothing in front of x squared. So we're just going to go starting at our vertex over 1, up 1, and then go over 2, up 4 times a. Well, it's going to be 1, 2, 3, 4. And then over 3, up 9 times a. Well, that's just going to take us up to here. And then, of course, you just make it symmetrical on both sides. Bingo, bango, bongo, right? Graph that as much as I can. Good enough. It's a little shaky, but it'll work. Keep on going here. There we go. Good enough. Now, how can you tell that the inverse of f of x won't be a function? Well, hopefully you see that this f of x is going to fail the horizontal line test. If I were to draw a horizontal line on this, it's going to go through more than once. So the horizontal line test, HLT, it fails, right? Now it says graph f negative 1x on the same grid. Easiest way to do this once you have a graph already is just pick your x and your y and swap them, right? So I'm going to move this point first. 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. Negative 1, 2 becomes 2, negative 1. And then we can pick this point. 2, 5 becomes 5, 2. Negative 2, 5 becomes 5, negative 2. And then these last ones up here, I'll just give you a second just to kind of get caught up because I bet that went pretty quick. This last couple points over here, we have 3, 10, right? 3, 10, that's going to become 10, 3. And this one over here, negative 3, 10, that's going to become 10, negative 3. And then, of course, connect that as much as you can. Good enough for me. I know I goofed. Yeah, I know, you know what I was going to say. Good enough. I goofed too much. I goofed too much. There we go. That's better. So that's my inverse, f negative 1x. So describe how the domain of f of x could be restricted so that the inverse of f of x is a function. Just to drive this home right now, this is a really good final example. You want to chop off one of the arms of the original blue function f of x. Look at your vertex. Your vertex is at 0, 1. Just pick one of the arms to keep. I always keep the positive side. So if I'm going to restrict one of the arms here, I'm just going to say x is going to be greater than or equal to 0. So x is greater than or equal to 0. Whew, that was another long lesson. Holy smokes, this whole chapter 1's been long. Don't worry, later on in the course, things get a little quicker. But for practice today, you can now complete the chapter 1 assignment. You can do that whole darn thing, right? For other additional practice questions, because believe me, you should get some extra practice, page 51, questions 1 to 7, and then 12. We are now officially done chapter 1. Yay, awesome, right? So really good news, chapter 1's all done. We'll have some mixed review next class. I haven't decided yet if I'll make that a video or if we'll just do it live, but it is what it is. The focus will be on checking for your understanding, so be prepared to be pushed a little bit. The next lesson is going to be a little tough. I do have a chapter 1 review study guide to give you too. Make sure you get that from me. It might help you as a what you need to know type of checklist. Some people like it, some people don't. It is what it is. Anyway, as always, if you have any questions, please let me know.